So let's go through Newton as he was deriving his universal gravitation. From what everyone knew, Newton as well knew that the force of gravity on, say, this little apple at the surface would be proportional to the mass of the apple times the gravity at the surface. But they didn't know if the gravity at the surface, the acceleration at the surface, was going to extend all the way out. But what this means is that the force of the moon is equal to the mass of the moon times g at the moon. So the other way that we can put this, we could say the force of the moon is proportional to the mass of the moon. Since we don't know the g at the moon, we can kind of just talk about that. But we also know Newton's third law, which would say the force on the Earth would be proportional to the mass of the Earth. So in order for these two to happen in conjunction then their force of universal gravitation would have to be proportional to both the mass of the moon and the mass of the Earth. So we have that, but we don't know what's happening with this g at the moon, and this is where the real experiment with the apple and the moon kind of works out. So as Newton is thinking about this, he thinks that, hey, there must be an acceleration at the surface, right? And we know that acceleration at the surface is 9.8 meters per second squared. And it might be that the distances, right, that this distance compared to this distance will matter about it. So he knows that the acceleration or that the radius at the surface is 6.4 times 10 to the 6th meters. Now, he doesn't know the acceleration the moon feels just yet. We'll find that out. But he does know the distance the moon is away, 3.84 times 10 to the 8th meters. They found this through Eratosthenes' experiment. They found this through eclipses and transits. And so then, what could he do? Well, he knows that the moon is moving in a circle. So the acceleration of our moon is equal to the radial acceleration, and we can just use circular motion. So this would be r omega squared, or r times 2 pi over capital T squared. So if we have this, we know the period of the moon. We've been able to measure it quite well. Here we have that it's 2.36 to 3 sig figs times 10 to the 6th seconds. So if we plug this in, our acceleration of our moon is going to be the radius from the Earth to the moon, 3.84 times 10 to the 8th meters, times 2 pi over 2.36 times 10 to the 6th seconds, quantity squared. And I'll spare you the calculation, but you can put it into your calculators as you want. And you should get 2.72 times 10 to the negative 3 meters per second squared. So we can kind of fill that in here now if we want. Well, if we look at this, and if we're, right, a physicist back in the enlightened times, one thing that might be very interesting to look at would be a ratio. To look at the ratio of, right, the acceleration of the moon over the acceleration of the surface, the acceleration of the surface of the acceleration of the moon. So if we do a sub s over a sub m, that would be 9.8 meters per second squared over 2.72 times 10 to the negative 3 meters per second squared. So give this a pause, see if you can calculate it. All right, welcome back from the pause. You should be getting something around 3603. So to 3 sig figs, this is 3600, right? We might have some other weird math going on in that. In addition, let's take a look at this radius. So the radius of the surface over the radius of the moon is going to be 6.4 times 10 to the 6 meters over 3.84 times 10 to the 8th meters. Feel free to pause this right now to calculate what this ratio should be. Okay, so if you've done that, then you should be getting a really ugly number, or a little bit easier is if we did 1 over 60, right? This is about 60 times more. Now, do we see a relationship between 3600 and 60? Newton certainly did. He said if he squared this, Rs over Rm squared, then you get 1 over 3600. Looking at this a little bit differently, we can then kind of combine these two and look at As over Am. Well, this would be 1 over Rs over Rm squared. So we can do a little bit of funny little math, right? 1 over Rs squared, we can then have just be stay on the bottom, or we can move this all the way up top, but we can also do a little bit more tricky of stuff. This should be then 1 over Rs quantity squared, and this should be 1 over Rm quantity squared. So what this is saying is it's saying that our acceleration is proportional to 1 over the radius squared. So now as we're looking at our force of universal gravitation, bringing this together and this together, since our acceleration and our force should be the same, now we have that our force of universal gravitation should be proportional to the mass of the actor, the mass of the recipient, over the radius squared. And the last thing that brings it all together is this universal gravitation constant. Since Newton didn't know the mass of the moon, and Newton didn't know the mass of the sun, didn't know the mass of any individual planet, he was unable to find G until Cavendish, a number of years later, was able to do a very interesting experiment, and we found, FUG is equal to G MA MR over R squared, and it's a vector